All right, so to start off, why don't you take a moment and looking at this diagram of an LSTM, try to talk to your neighbor and explain what is happening in these first two gates of the LSTM. All right, does anyone want to take a shot at explaining what is happening in this first gate with the first yellow sigmoid? Yeah, Jacob. It's the forget gate. Yes, exactly. So yeah, you want to explain maybe step by step what's happening in this plus block, and then what's happening in the sigma block, and then what's happening in this multiply node? Yeah. Yeah, great. Yeah, so just to reiterate that a little bit, we're going to add or concatenate each of our input, our previous hidden state, and our previous memory, which is CT minus 1. And then we will multiply each of these by a weight vector, and then follow that by a sigmoid. So we have two options. Option A is we concatenate and then multiply that entire block by a weight matrix, that entire concatenated vector by a weight matrix, followed by a sigmoid. Or we can multiply each of these individual xt, ht minus 1, and ct minus 1 by its individual weight matrix, and then add them together. So it's either concatenate then weight matrix, or weight matrix then add. Does that make sense? And then follow that up with a sigmoid activation, which smushes those values between 0 and 1. And we can think of that as a gate because numbers that are set to 0, when we multiply them with the memory vector, the 0 entries will basically forget those entries of the memory vector, and the 1 entries, the 1 outputs of the sigmoid function will remember the memory. All right, great. Anyone want to take a shot at this second block? Yeah, Brendan. Yeah, so we were calling this first gate a forget gate. We're calling this the second gate a remember gate, and that's the right intuition. Yeah, what do you think? Yeah. That is a great question. So yeah, he brings up the point that couldn't you just take the opposite of the forget gate and make that your remember. And in fact, we will see the next thing we're going to look at does exactly that. So good thinking. If you had come up with that idea 8 years ago, you could have written a great paper about it. But yeah, you're totally thinking along the right lines. Yeah, so for this remember gate, we're again going to learn a function of what to remember and what to discard. But this time, we're going to be remembering and discarding our transformation of our input. So you'll notice that this third plus block takes as input only the xt and ht minus 1 and does not take as input ct minus 1. And that's because we want this purely to be adding new information from our current input. So then we transform that with a tanh activation and then multiply that by that sigmoid gate, which will set certain entries equal to 0 and preserve others. And then we will add that on to our memory. Any questions up to here? Yeah. Not that I'm aware of. I'm not aware of I mean, generally sigmoid is a bad activation because it kills gradients. I'm not sure why we're using tanh as opposed to any other. Yeah, I'm not aware what like. Good question. So why are we using sigmoids if they kill your gradients? And the answer is because there's number one, there's a really nice interpretation to what's happening. They have that bound at 0 and 1, and also the main information flow of our network is not through the sigmoid activations. It's through these tanh activations. Okay, cool. So we have forgetting and remembering covered. Now, what's happening here in this last block? Well, we are going to, again, learn a third gating function. And this gating function will operate on CT, our memory vector. And what it will do is it will basically forget and remember some information of CT to be used as our current hidden state, HT. You can think of that, I think of it intuitively as basically how much of our memory is relevant to the current step of classification or whatever we will use this HT vector for. So for example, if we're working on natural language, HT might be used for tagging parts of speech. And so this is just a transformation that says, how are we going to take information from our memory for our current task. So that's the LSTM, but that's not where it ends. Oh yeah, and so this is just another representation of the same thing, but in math. I'm not sure it's necessary to go over this. Yeah, well, we went over that in pretty good detail. Okay, so if we're going to, I guess, complete this diagram, make a complete graph, we're going to then wrap this HT around to be the HT minus 1 of the next LSTM block, and same with the CT to become the CT minus 1 of the next block. And then we use HT for classification or whatever auxiliary task we have going on. This is just rewriting the same thing, except unrolling the LSTM across the page. So that's not the only way that we can use an LSTM, however. We can also stack LSTM layers. So in addition to unrolling across time, we can stack these LSTM layers within a certain time block. What that looks like is you take HT and pass it into another LSTM block, which produces another HT. And you can unroll those across time, similar to before. Can anyone think of why you might want to stack LSTM blocks deeper? Yeah, Jane, you want to take a shot?
Probably.
Totally. Yeah. So that's a great answer to reiterate for the recording. Yeah, just it allows us to go deeper and learn a deeper hierarchy of features, allowing us to recognize more abstract concepts. Yeah, Dane. Yeah, that's a good analogy. I like it. Okay. All right, so that's not the only thing we can do with LSTM blocks. So we can also make RNNs bidirectional. So if you remember, I mentioned a couple of classes ago how a problem with RNNs is that over long context windows, they tend to forget things. They tend to forget things at the beginning of the sequence. And that's why LSTMs, long short-term memories networks were invented, was to try to preserve some information over longer periods of time. However, you're still limited in the amount of information that you can fit in a 200-dimensional vector that's basically has the task of summarizing the entire context that you have seen so far. And so for that reason, some researchers came up with this idea of bidirectional RNNs, where you have two LSTM blocks that start on opposite sides of the sequence, and they gradually move towards each other. And so so let's say we're doing this part of speech tagging again, and we're trying to classify the parts of speech of words in a sentence. This allows, you can imagine that let's take, for example, what would be a good one? Can you think of a word that has multiple parts of speech? Okay, yeah, great. Yeah, let's take the word perfect. Okay, so if we were to use a unidirectional RNN and we were trying to do part of speech tagging on the word perfect, it would have to make do with information only on one side of that word. And so basically you don't have enough information to tell what part of speech the word perfect is. However, if we have another RNN, another hidden state bringing information from the end of the sentence, we can take our hidden state from the beginning of the sentence and that came from the left and the hidden state that came from the right, concatenate them together and use them together to classify the part of speech for that word. So there are a couple of problems that this solves. One is the fact that RNNs normally can only look in one direction. And the other is that trying to remember things for that problem of trying to remember things for a long time. So that's bidirectional RNNs. So this is just another example of a possible task. So in this case, we could have a question answering task where we have an encoder decoder RNN architecture where the encoder this would be a many-to-many task. So the encoder summarizes the question, and then the decoder decodes an answer to that question. Yeah, question. How words are varying lengths. So in this case, this is I don't know if this answers your question, but this is a word level tokenization that we're showing right here. So each word has its own basically entry in our vocabulary. So words are not varying lengths. If we were to go on letters, then we could have a variable number of encoding blocks and a variable number of decoding blocks. Does that answer your question? Okay. But yeah, the question is, can we do better? And so we introduced the gated recurrent unit, which does exactly what you were saying in combining the forget and remember gates into one. Let's take a look at how that works. So this is, in the middle, is one gated recurrent unit. It's an alternative to the LSTM as basically what happens inside that black box of your RNN. The way it works is you have one gating function that takes as input your hidden state and your current input and concatenates them, applies a weight matrix and then a sigmoid activation. And that becomes, let's see. I have to remember this. Yeah, okay, let's try to figure out where our remember and our forget paths are here. So our remember path is going to be through here, through this tan H. And so yeah, okay. Here we go. This diagram is a little difficult because it's not completely apparent which way the lines are going. But so okay, this sigmoid, this first sigmoid on the left is both our remember and our forget gate. And so our memory from xt, or our input from xt, comes into this tan H function via this purple line, and then is multiplied by 1 minus zt, where zt is the output of this gating function. At the same time, we have ht minus 1 coming from this top blue line, and that is multiplied by zt. So this transformation of xt is multiplied by 1 minus zt, and ht minus 1 is multiplied by zt. And so you basically have an inverse relationship between remembering new information and forgetting old information. Does that make sense? Okay, good question. So then where does this second sigmoid come in? And I was wondering about this too when I was reviewing for today's lecture. So in the GRU, they actually combine a portion of the previous memory, ht minus 1, with the current hidden state in their remember function. So I don't have a good answer for you of why that is, because you would think that it would be sufficient just to remember. You wouldn't need two paths to remembering information from your memory. But that's how the architecture is. So we have two paths by which we can remember ht minus 1. One is through the direct path, and then the other is through this tan H path that also gathers information from our input. So that's the gated recurrent unit. It condenses the memory and the current hidden state into one vector and combines the remember and forget gates into one. And that's really all you need to understand about the GRU. Any questions? Yeah. Good question. So yeah, great question. So the question is, do you, Like, does the gradient flow each time that you output a word? And so I would remind you of the difference between training and inference. So at inference, we're generating one word at a time, but during training, there's only one word that we are predicting. And so for training, the loss for that one word comes back, and it will hit the weights in this recurrent unit multiple times. There will be multiple paths leading back to those weights because of recurrence. But it still works out with gradient descent that they get updated. It just ends up being a sum of gradients across the different number of times that you've unrolled. Yeah, question. Yeah, so like a many to one problem. You give it the correct answer for previous words that it has seen in the sequence. So I think I understand what you're asking. So at training time, you always know all of the words leading up to that last word in the sentence. And so those are not predicted. Does that answer your question? Okay. So this is the math version of the GRU. Yeah, it's just the math version of the computation graph diagram that we just saw. Are there other alternatives? Yes. This is a paper that does a brute force search over RNN units and finds some alternatives that are marginally maybe better than GRUs and LSTMs. So there's that. Yeah, there are a couple of practical issues with training LSTMs. This is related to the difficulty of training forget gates, and actually, yeah, talking about the problem of vanishing gradients. And so you can simply, basically the problem is if you start out with your forget gates, the inputs to them being super negative, then the outputs of all of your forget gates will be 0, and you won't have a lot of training signal. So the solution is to add a small bias term. Yeah, so that's just a training trick. This is another paper that did some ablation testing where they basically blanked out different parts of the LSTM architecture and found that basically the most important gates are the input gate and the forget gate. The output gate is not super important, which we saw that I believe the GRU discarded the output gate. So just some interesting experiments that people have run in evolving this architecture. Okay, so some applications of RNNs and LSTMs. So this is, we've been talking a lot about using these on text. Now, however, we're using them on handwriting. So still text, but not really. So in this case, our inputs are X and Y coordinates of pen strokes. And we are trying to predict the relative X and Y coordinates of the next pen stroke given the current location. Well, given all of the pen strokes leading up to the current pixel. So these are a couple of examples of generated handwriting. You can see that they, on the left, we have training samples. And then on the right, we have handwriting or generated samples. So these obviously spell words, editorial dilemma of the tides in the affairs of men. And here we have these things that kind of look like words. That looks like cold wine. And then some things that look like handwriting, but maybe not words. Yeah, so this is some more details on that architecture. We're not going to spend a ton of time on that. So if you remember, we talked last class about this idea of temperature. So does anyone remember what temperature means in the context of sampling from an RNN? Yeah. Totally. Yeah, exactly. Temperature measures, yeah, how deterministic or how alternatively how random your predictions are going to be. And so high temperature corresponds to high or low randomness. High randomness, and low temperature corresponds to low randomness. So which of these handwriting samples, which of these do you think was generated with a high temperature and which was generated with a low temperature? Yeah, Josh? That's right. Yeah, the high temperature, more kind of scrawly handwriting is at the top, and the low temperature or is at the bottom. Yeah. I believe those are biases. So it's kind of like inverse temperature. Yeah. And we already did that. This is another architecture very similar to the handwriting generation architecture, except they used it to draw sketch art. So the data is about 70,000 images per class, and they trained a sequence-to-sequence variational autoencoder, which we will talk about later, but with an RNN architecture. So that's the architecture, and then here are some samples. So this is kind of interesting. So they used, again, an encoder-decoder architecture. And when you do that, you condense all of the previous input into a single vector, and then you decode an output from that vector. And what they found is that when you do that, you can actually add those representation vectors together. And so they trained this sketch network on lots of different classes, and then they tried adding the basically doing arithmetic with these representation vectors. So here we have a cat face plus a pig, a whole pig minus pig head, and you end up with a cat head on a body. So you can add body parts by doing this latent space arithmetic. Similarly, we can take a full pig, add a head, or add a cat head and subtract a full cat. So cat head minus full cat, I'm guessing, is like a negative body. And sure enough, that deletes the body from the pig. So yeah, kind of interesting experiments. So here is sketch RNN predicting possible completions of different sequences. So it's given this starting sequence, it tries to complete. So in the top we have, looks like we're drawing some trees. Next row, we're drawing some faces. Third row, we're drawing an owl. And yeah, you can see that it does pretty well. And it does that simply by taking this as input and just using the RNN to predict the next pen strokes. We're gonna quick demo. Okay. I'm gonna make sure the screen share is working. Okay, so which model do we want to choose? We want to do one trained on cruise ships, palm trees. What do you think? Scorpion. All right, so we're going to start the drawing and it will autocomplete. What's happening here? Okay, well, we'll try this. So let's draw a claw. Oh, here. That is what it looks like, isn't it? All right. Well, yeah, it looks like it's still trying to draw a garden on top of my scorpion claw. So we will come back to that in a bit. Sorry for these technical difficulties. Okay. All right, so this is another, we'll come back to that later. This is another task. This is neural image question answering. So we did image captioning before. Now we're doing image question answering, which is very similar. We have conditioned on representation of an image that comes from a CNN. We prompt it with a question, and then it responds with the answers to the answer to that question. And so in this case, yeah, they're teaching the LSTM to look for objects in images. And interesting. These are some of the results. So here we have an image of a office, and we're asking what is on the right side of the cabinet, and it answers the bed, and that is correct. You can see on the right side of that cabinet is the corner of a bed. Here's a question about the number of drawers in this dresser. The neural image question answering answers 3. Oh, and actually, sorry, the language only is based on is not conditioned on the CNN image, okay, or on the CNN representation of the image. And so this is basically just using language to try to figure out what you want to say next. And so the comparison is showing that when we condition on images, we can do much better at answering questions about images. So yeah, in what is on the refrigerator, just purely by language, it's able to guess that a magnet and paper is on the fridge, and sure enough, that is what is actually on the fridge, but just purely off of language. But you can see that the network is definitely taking some information from that image, as in this case, it is correctly identifying that this bed is blue and white, but it might actually be yellow and silver, just like the dress. I'm not sure. Okay, so generative choreography. So again, we're going to take a recording of contemporary dance with using a Connect sensor for detecting joints, and then we'll train an LSTM on it and see what we get. And this is the result. All right. Okay, well, this is too bad. We will move on to the next lecture and hopefully get back to those fun demos next class. All right, so newsflash, RNNs are not the best thing out there and are not used that much in practice anymore. They have largely been replaced by attention-based sequence models. So now we're going to talk about what those are. Okay, so these are kind of the big ideas. So we're talking about neural machine translation. This is where the idea of attention was introduced. Neural machine translation is abbreviated NMT. And so as compared to previous statistical-based methods, yeah, there was a lot of hand engineering of features, syntactic analysis, but ideally with deep learning, the main attractiveness of it is being able to train end to end and yeah, not have any human intervention in that loop. The common metric for measuring performance on neural machine translation is called BLUE score, which basically compares your translation with a reference phrase with a sort of intersection over union metric. So just a preview of where we're headed. So we started with sequence-to-sequence models and RNNs. We're going to introduce attention-based RNNs and we might skip over fully convolutional architectures. I'm not sure. That's basically, that was an idea actually that someone came up with when we were talking about how to handle variable length sequences. You can use one-dimensional convolutions. I'm not sure if we will get to that in this class, but yeah, kind of the main phylogeny, if you will, of the current state-of-the-art networks goes from RNNs to attention RNNs to transformers. And that the architecture on the bottom right is a transformer. Okay, so let's take a look at this neural machine translation task. At this point, you are probably familiar with this type of diagram where we start with an RNN encoder and then condense that into a single vector and then use an RNN decoder to produce predictions. So during training, we have correct translations available. So our training items will be, I am a student _ and we're predicting je. I don't speak French, so please pardon my French. Then the next training item will be, I am a student _ je, and we will try to predict Suisse. And then our next training item will be, I am a student _ je Suisse, and then we're trying to predict étudiant, and then finally predicting the end token. And then at test time, however, we do not have access to the labels. And so we will start with this beginning token, and then whatever it predicts for the first token will be fed back in, and we'll predict the next, which will be fed back in, etc. Does anyone feel like they're still kind of hazy on training versus inference for RNNs, or do you feel like you understand the distinction? Yeah. Yeah, totally. Yeah. So if we're doing inference, the longer we go out, yeah, that we're going to probably have this cascade of errors because we will be basing our predictions on other predictions. Okay, so a difficulty of RNNs is that, yeah, you have to handle this sentence length problem where it might be tractable in the case of a sentence that's only 6 words long. But what if we're trying to translate an entire Wikipedia article and we have hundreds or thousands of words? Yeah, the path length is proportional to the length of the input plus the output. And so there's a pretty groundbreaking paper by Bodenau in 2015 where they introduced this idea of attention. And you can see that as sentence length increases, normally RNN performance peaks and then flattens out and starts to degrade significantly once sentences get longer than about 30 words. However, with attention, there is no performance degradation with sentence length, which could be pretty impressive. Yeah. Is there a number assigned to what? Good question. So I'm going to say we're going to circle back to that question. So that's a great question. How do we deal with unseen words in the vocabulary? And that's a question that applies to RNNs. That's a question that applies to attention RNNs and then to transformers later on. The quick answer is that, yeah, if you have a fixed vocabulary size, then you won't be able to handle new vocabulary words. And so they use these things called word embeddings as basically fixed length word representations that can handle an arbitrary vocabulary size. And each word in the vocabulary is just a different vector in this 100-dimensional space, as opposed to a one-hot encoding, where the length of the one-hot encoding is fixed based on the size of your vocabulary. Okay. Yeah, so attention looks like it basically solves our sentence length dependency problem, at least up to 60 tokens. So how does it work? Instead, when we predict the next token, instead of forcing our network to memorize the entire preceding sequence into a single vector, we are going to allow the network to have a random access memory in which it's able to look at the representation of each of these previous hidden states without reducing them all into a single vector. So to do that, we are going to compare the target hidden state with each of the preceding vectors, or each of the preceding hidden states, and assign a score to them. And so you can see that, and any ideas what you might use for a score function? Dot product? That sounds like a great idea. Yeah, that's an option that is used sometimes, is a dot product for a score of similarity or compatibility between the current hidden state and each of the previous hidden states. Then we normalize those to probabilities, and then we create a new a unique summary vector for each token to be predicted, which is a weighted combination of all of the previous hidden states. So previously, we had to basically have the same summary vector for each new token that we wanted to predict. Now we can create a custom summary vector based on the token that we want to predict. And we will pause there.